Hi. Today I want to continue my conversation of wave optics. Today I want to talk a little bit about diffraction grating. And last time we talked about the Young's double slit experiment, where we sent light through two parallel slits. A diffraction grating is like that, except for instead of two parallel slits, we have many, many parallel slits. And so today I have holographic glasses. You may have seen these. These get given out as freebies at various events, especially sciencey kind of events. These are from the Little Shop of Physics, and if I put these on, and I see rainbows everywhere, rainbows. It's because this is a diffraction grating. Now you can't see them. And if I hold it up here, hey, it doesn't really work there either. A little bit. Oh, you can kind of see it. A little bit. That's the best rainbow I've gotten. Oh, just a little bit down there at the edge. Oh, let's see if I can get it again. Oh, there we go. Yep, there you go. See, just a little bit of a rainbow there. When I looked through these, I saw those rainbows all over the place. And so this is basically the same idea. We get the light coming through these many, many slits, and where it adds constructively for red light, we see a red spot. And where it adds constructively for green light, we see a green spot. So last time I demonstrated, or tried to, I suppose, what it looked like when I shone my red laser, or excuse me, my green laser through the double slit. Let's see what happens when I show my green laser through the diffraction grating. So now I'll shine my laser pointer through my diffraction grating, and you can see that we just get a number of discrete dots. And here I'll bring it a little bit closer to my screen. And yeah, we can see what? I can see 1, 2, 3, 4, 5 on there, and there's two more way off to the side that you can't see on the screen here. So at diffraction grating, the math is very similar. And it's the same idea, but now we have many, many, many slits. And so it's much harder for the light from all of those different slits to all add up constructively at the same location. And so it's a much more constrained problem. And so that's why instead of seeing just a smear of a whole bunch of dots, like we did through two slits, instead we see these very discrete individual dots. Because the light from every one of those slits has to show up in phase at a certain location in order to see a bright spot. To give you an idea, these, I believe, these glasses that I was looking at, yeah, here, we can see it here. Maybe you can read that. I don't know if you can. When I put paper in there, sometimes it just looks like a whitewash. It has 500 lines per millimeter, it says. So you can see that that's very, very small, 500 lines per millimeter. So that means each line, each little gap is separated by 1/500th of a millimeter. That's only 2 microns, so that's pretty darn small. Okay, so again, same idea though. All of the light from every slit has to arrive in phase. The path length difference is different for every slit. When that all adds up constructively, we see a bright spot. And it turns out the math is identical to the double slit. It's just that we get these real discrete lines. And instead of D now being the spacing between two slits, now it's the spacing between our many, many, many slits. Notice here they are not equally spaced. And as you may have been able to see when I ran my light through the diffraction grating there, it spreads out much more. And so typically the small angle approximation is not going to serve us very well when we are talking about diffraction gratings. But we still label the central maximum here as m equals 0. We get m equals 1 on either side, m equals 2, and so on. The math, again, looks just the same. Here, D is the spacing between the slits. And now we can say the mth position, the y position of the mth maximum is given by this equation. Again, y is the distance from the central maximum to whichever maximum we're talking about. And the integer m is called the order of diffraction. Once again, L is the distance between our diffraction grating and our screen, and theta is the angle that they arrive at. And again, the angle from this central maximum, I should say. So we see much sharper, brighter, more distinct lines when we increase the number of slits. And so we saw these, with n equals 2, we kind of saw this fuzziness where the bright spots were sort of smeared out. As we increase the number of slits, though, we see that they get sharper and more focused and brighter. And this is n equals 50, right? Remember, these glasses I had have 500 per millimeter. So, if that's 20 millimeters across, that's, what, 10,000? That's a lot. Happens all the time in real life. Here's diffraction from a feather. This is an image taken looking through a feather. And if we're to zoom in on this feather, there's all these little barbules, which are very closely spaced. Their spacing is on the order of the same size as the wavelength of light, and so we get diffractive effects. You can see this yourself. Next time you're out in the evening, look at a street light and slowly close your eyes. And what you'll notice is that the light spreads out. It does not spread out in this direction, which we might think, because that's how my eyelid is oriented, right? There's a slit like this. As I close my eyes, you'll see the light spreads out in this direction, because it diffracts as it goes through your eyelid. Try it out. It's pretty sweet. A reflection grating works exactly the same. And I actually showed you this when I showed you the CD in the last video, but you ought to be able to see sort of a rainbow in there, and you kind of can if I hold it just right. There's a little bit of a rainbow down there. And indeed, that is the exact same math. It's just here, there's a number of ridges on the CD, and as the light reflects off of that, we see it constructively adding where we see those bright colors. And we can see a similar effect if I bounce my laser pointer off of it. And so if I bounce it off of here, we ought to see some spots. Let's see if I can. And indeed, yeah, you can see them a little bit there. There's 2 spots. With my eyeballs, I can see a few more than that. Kind of one up there by my cloud. It's kind of in and out. Anyway, we can see some real distinct spots when I bounce that off of my laser pointer. Same exact math. It's just whether it's reflected or passed through the grating. Beetles and other animals use this structure for color. That's sort of where we started off this chapter, was looking at a hummingbird that uses this structure to develop color. Here we see a beetle that's doing that. And so here we see this beetle has been hit with a white light right here. There's white light shining right here. And what do we see? We see reflections of multiple colors. And what we're seeing here is 2 different orders, right? So here is the M equals 1 blue stripe. Here's the M equal 1 green stripe. So this is where the green is adding constructively for M equals 1. Here's M equals 1 for yellow, for red, and now we're into the M equals 2 line, M equals 2 rainbow. Here's the M equals 2 blue, here's M equals 2 green, here's M equals 2 yellow, and here's M equals 2, kind of a pretty magenta color almost, and we can almost see the startings of the M equals 3 rainbow also, but only just barely. And what's pretty cool is that you can use this idea to learn about the structure of the beetle. So, and this is real data from a real research paper. So, a researcher illuminated a specimen of ground beetle with a beam of yellow light, which had lambda, that's the wavelength, of 570 nanometers. The resulting diffraction produced clear maxima at 13 degrees and hit 25 degrees. What is the spacing of the ridges that produces this diffraction effect? So we can use these measured angles to figure out what a beetle's shell is like. That's pretty cool. So let's write some of this information down, and we'll go from there. Okay, so we've got a maxima at 13 degrees and 25 degrees. Now, they didn't tell us specifically, but we have to just assume that these are the first 2 orders. So this must be M equals 1, and this must be M equals 2. Okay, so now we can just look at our equation for diffraction grating, and that says that sine of theta m equals m lambda over d. So let's just see what we get when we solve this problem. Okay, so the first thing we need to do, we're trying to find the spacing of the ridges. So the thing we're looking for is the spacing between the lines. That would be d. So solving this equation for d, we get d equals m lambda over the sine of theta. So for m equals 1, we get and what would be different if we were doing the m equals 2? Well, we would just plug in the different m equals 2 and our different angle. And so now we run our calculator, and we get 2.5 times 10 to the negative 6th meters, and 2.7. Well, wait a minute. Why'd we get two different answers if there's only one beetle? There's only one spacing for the lines, right? Well, because this is a science experiment. And as you can see, by looking at that beetle, it's kind of hard to measure exactly what the angle is that it's coming off at. So this is real data from a real paper. What's our best guess? Oh, I think our best guess would probably be 2.6 micrometers. We'll take an average of the two. So that seems pretty reasonable. There's our 13 degree, m equals 1. There's our 25 degree, m equals 2. And again, this is real data from a real research paper, so I'm not surprised.